I'm going to talk about data access at the speed of LightBits in an open programmable infrastructure world. I'll explain what that means. So to begin with, let's talk a little bit about a standard Kubernetes deployment today, where we are a storage company, and this talk is going to be focused on storage. So from the storage perspective, such a Kubernetes deployment today may look like this, where you have your application, maybe CockroachDB, maybe MongoDB, maybe Cassandra, maybe something else that's running in Kubernetes containers. And those containers are using local NVMe storage because they need, fast access to their data. This has some advantages. For example, you get local flash performance, but it breaks the application and Kubernetes philosophy of portability between platforms because the data is now local. The data in the pods are assigned to one physical server, and if that server goes down, and as we all know in the clouds, anything that can fail will fail. So when that server fails, not if it fails, when that server fails, all of that data is now gone and it has to be replicated. It had to have been replicated in it previously, but it now needs to be sort of, the pods and the data need to be spun up elsewhere. Pod movement is limited or not allowed because the data is local. If only some of your Kubernetes nodes have local NVMe drives, then now your service portability is limited. And if all of your Kubernetes nodes have local flash, then what we're usually saying is that results in pretty poor utilization because not all applications need it. So in our world with LightBits, we actually prefer a different model. And all of this is, by the way, is just background. So to give you all context to what we did with IPUs and what we'd like to do with IPDK. I probably should have started from that just to sort of set the expectation. This talk ultimately is an IPDK wish list. We've had some experiences with SmartNICs, with DPUs, most recently is with Intel's IPU, Mount Evans. And obviously that all predates IPDK. And what we thought might be most useful for this talk and for this event is just to explain what we've done and what we'd like to do with IPDK once it's further along. But of course, we look forward to contributing to the effort. So what I'm talking about now is just background and context for what will come in a little bit. So in a LightBits world, those same Kubernetes worker nodes that are here on the left, they run the same applications, they run the same, it's the same Kubernetes cluster, except they're all connected to the remote storage via NVMe over TCP. At LightBits, we were one of the initiators, no pun intended, of NVMe over TCP. We standardized it together with many others, Facebook and Intel and Cisco and many others. And what we provide, LightBits LightOS, is software-defined storage that runs on standard servers and is accessible or exposes block storage to compute servers. Can be Kubernetes worker nodes, can be OpenStack, can be VMware, doesn't matter, can be something else. The important thing is that it's all accessed via standard NVMe over TCP over standard TCP IP networks. And there's, in the Kubernetes case specifically, there's a CSI driver, a Kubernetes CSI driver that sort of orchestrates the whole thing. So this is the world without IPUs or DPUs or SmartNICs. I'm just going to use IPU from now on, and I don't mean specifically Intel's IPU. I just mean any infrastructure processing unit. So this is what the world looks like without IPUs. This is what the same setup would look like, or the same world would look like with IPUs. Now it's the IPU that's performing the NVMe over TCP access to the storage cluster. And the local nodes see local NVMe devices surfaced to them by the IPU. This is a very appealing model because of many reasons. One reason could be due to the lack of NVMe over TCP support in the host software. Although today you can find NVMe TCP support in Linux, of course, and starting with the latest VMware ESXi release with VMware ES6i, Windows doesn't have good inbox NVMe TCP support. The BSDs don't have good NVMe TCP support. I'm sure there are many other environments, too many to name, where NVMe TCP support is lagging. However, pretty much any modern operating system or hypervisor will have good local NVMe support out of the box. So if we've removed the need for NVMe TCP and replaced it with just the need for local NVMe, we've just made it possible to run on many different environments. And there are other reasons as well. For example, NVMe over TCP is fundamentally a TCP/IP-based protocol. There is network processing to be done. If we can offload that from CPU cores that could be more profitably used to run application workloads and offload that to more specialized, accelerated environments such as an IPU, then that is also a win. There are security aspects, there are manageability aspects. So many reasons why we might want to use IPUs on the compute nodes, or clients as I'm calling them here. And of course, that's just the hardware. Let's talk about where the software comes in. But before I go there, I want to mention one thing that I will not talk about, although that's also an interesting subject and a use case where we'd like to see IPDK play in the future, and that's using IPUs on the storage targets. In the LightBits model, the storage targets are just standard servers, can be exactly the same servers as the Kubernetes worker nodes here. The only difference would be that the servers used as storage targets would usually have many SSDs for I think the obvious reasons. These are storage serving servers, but they can be completely standard servers, and they may be equipped with an IPU, or the server may be an IPU. And those are two very interesting usage models that we're also exploring, and that we hope that IPDK can be relevant to in the future, but I will not talk about them today. Today, I'm just going to focus on the more straightforward setup where the compute clients or application servers or Kubernetes worker nodes are equipped with IPUs, and we'd like to use IPDK to drive it. So a few months ago at Intel On, we've done a demo with pretty much what I just showed you, and there's a nice 5-minute video online. The link is here, and I can send it offline to anyone who's interested, on where we explain exactly how this works. What we did in this demo, I'm not going to go through it right now. I'll just mention the different components and then start talking about what's missing, or what we did, let's call it manually in the demo, and would like to do in a more, I'm not sure what's exactly the word, more automated or more structured way with IPDK, and more portable. That's important too, because we'd like to do it on every kind of IPU or DPU or SmartNIC, not just the Intel Mount Evans IPU that we've used in the demo. So, there was a Kubernetes cluster with a CSI driver that was orchestrating the whole thing, NVMe TCP for the data path, including discovery, that I'll talk more about it. We used the Mount Evans IPU, and of course, there is the storage cluster that was running LightBits, and the Cassandra containers pods that we were running were saw what looked like local NVMe devices, but were actually remote NVMe namespaces backed by the LightBits targets. So I want to talk about, let me just quick time check here. I want to talk about, sort of the fundamental operation for this demo, which is how do you get the host software or the containers running on the host to access the storage cluster? What needs to happen? And these are the steps that needed to happen, okay? Initially, the Kubernetes CSI driver contacted the storage cluster, the LightBits storage cluster. This is done using gRPC, but it could just as well have been done over a RESTful API. It doesn't really matter. There's a control plane operation here or a management operation to create a volume, okay? A volume in LightBits is an NVMe namespace. It's not mapped to the drives directly. There is an abstraction layer. There are all sorts of data services, but it is surfaced outside of the storage cluster as an NVMe namespace. So the first step is to create that namespace. That namespace, and this will become important in a second, is uniquely recognizable. It has a UUID or NGUID, doesn't really matter. There is a way to identify that namespace. Okay. Once that happened, the volume has been created. The IPU has to discover that volume. NVMe over TCP and NVMe over Fabric in general has a discovery mechanism. And with that discovery mechanism, the storage cluster you can learn about the storage cluster, IPs and so on, and connect to it. This step is actually multiple different steps. I'm not going into the details here, but at the end of the day, after step 2 has run to completion, the IPU now knows and can access this NVMe namespace on the LightBits storage cluster. But we also need the host software to access it. To that effect, the IPU goes and creates or surfaces to the host software an emulated local NVMe device that will, in the next step, be mapped to this remote volume. This today, at least in the Mount Evans demo that we did, happened through low-level SPDK JSON RPC, if I recall correctly, commands let's put it this way, it worked, but it was a painful API, and I will talk about that in a bit. No offense to any SPDK folks. It worked, which is incredible, but it's not the sort of API that you would like to use in a large-scale production deployment. So, let's say the emulated local volume has been surfaced to the host software. Now comes a critical step, and that critical step involves the control plane, the CSI plugin in this case, including certain aspects of it that are running on the host itself, mapping the remote volume with the UUID X to the IPU's either physical function or virtual function Y, and that in turn has to be mapped to a local block device Z. So this step, without which there is no way to make this work, is crucial. And it is, as I mentioned, it required a lot of fiddling with a lot of moving parts in SPDK through the very low level BDEV JSON RPC API to make it work. Let's say we've made it work. What happens next? Well, the host software accesses for I/O, read, write the local volume via local NVMe. Those transactions go to the IPU, which converts them to NVMe over TCP accesses to the LightBits storage cluster. So, for example, if the host software performs sends an NVMe write command, that is converted into a write command to the NVMe, to the appropriate NVMe namespace on the storage cluster, and so on. So, as I mentioned, all of this stuff was working in the demo, and in the Cassandra application, the Cassandra containers were happily chugging along, accessing their persistent Kubernetes storage backed by the LightBits cluster. And by the way, the CSI driver the LightBits CSI driver that controlled all of this is open source. So I don't think we've published these specific patches, but if anyone is interested, we'd be happy to share them. But as I mentioned, it required a lot of fiddling, which leads me to my last slide. And we're sort of extrapolating from what we've from our experience with SmartNICs, DPUs, IPUs so far, and we've come up with an IPDK shopping list. This is what we'd like, and as I mentioned, we're also, of course, willing to contribute and help make it happen. So, starting with the very concrete example that I've just shown you, here's what we would have liked to have, shopping list or wish list. Here's our cluster's discovery endpoint. This is an IP and port. Here's the UUID of the volume we want. As I mentioned, volumes have UUIDs. Volumes meaning NVMe namespace here. Now surface it, the IPU, as a local NVMe device on the host connected to this PF or VF. So we basically like an API that will abstract all of the low-level SPDK version-specific BDEV JSON RPC into something that's much higher level. And once you're working at this level, then I think it should be pretty clear that it can be equally implemented on other IPUs, even if they're not using SPDK, even if they're running completely different software stack, even if they're implementing some of this stuff in hardware, because this is all standard. That's the important thing. How NVMe over TCP discovery works is completely standardized in NVMe TCP and NVMe over Fabric. UUID is just a UUID. Surfacing it as a local NVMe device, that's basically NVMe and PCIe. If we had an API that worked at the standard level, then it could be implemented pretty much everywhere. More broadly, or abstracting and going at a higher level of abstraction, what we'd like is a joint API that is common to most, if not all, SmartNICs and IPUs. And we'd like that API or sets of APIs, first of all, to configure access to remote storage. This is our bread and butter. But we'd also like to use it for deployment and provisioning of local services on the IPUs, for setting up VXLANs and network virtualization. And again, I'm looking at this from the point of view of LightBits, of disaggregated software-defined storage that's network attached, or accessed for control plane operations over gRPC or REST over HTTP over TCP/IP, for the data path via NVMe over TCP, There's internal TCP/IP-based traffic for volume replication, for resiliency, and so on. So we'd really like an API that enables us to configure and participate in whatever larger, data center networking schemes are going on. We'd like a way to work with IPsec. We'd like to have a way to work with data at rest encryption, decryption for storage. The data may not necessarily reside at any specific place, but a common API to configure what the user would like to happen to it would be very useful. Same for data integrity configuration end-to-end, for example, T10 diff. Again, this is something that involves many different actors on the I/O path, all the way from the host through the maybe the IPU on the host, then to the IPU maybe used on the target or that is the target, and then the target software, so and even the drives. So a common way to do that would be very nice. And for resource metering and limiting network storage, there are bandwidth and IOPS, quality of service capabilities that we provide. There's rate limiting. There are many things that it would be nice to have a common way of controlling, configuring, metering, and so on. And then maybe even for billing, because once you have metering and limiting, then billing sort of follows from that. So that's a high-level list of the different areas that from the storage perspective, and I fully recognize that there are many other perspectives. I'm just providing our view of the storage perspective here. We'd like support for controlling IPUs, both locally from the host and remotely from some centralized management layer. And this might entail and involve different management access transports. There might be security considerations. Is this trusted? Is this not trusted? How do you know who's allowed to do what, and so on? At an even higher level of abstraction or a meta level, we'd like the APIs to be as simple as possible, but no simpler. Key to this is clear and concise error reporting. Let's put it this way, and I'm not pointing a finger at any specific software stack or IPU or DPU or SmartNIC. We've seen some APIs that were far from simple. They may have been low level, but they were far from simple. So really, the APIs should be, I would hope, will be given the most scrutiny and the largest amount of brain power. Because if the API is correct and easy to use and simple and idempotent and just works, then the implementation can change underneath multiple times, but the API remains stable and useful, because that's what we want to do at the end of the day. And another aspect of this is robustness. We'd really like the APIs to be race-free and safe in the face of retries and crashes and outages and concurrent access. For those of you who are familiar with CSI and Kubernetes, this is not something that's nice to have. This is absolutely mandatory, because I mentioned that the CSI plugin sort of orchestrates everything. The CSI plugin itself is driven by Kubernetes, and Kubernetes will retry, will run concurrent instances of the plugin, will crash. There's nothing that we could do about it. So either you have to do an incredible amount of work at the CSI plugin to try and deal with it, because you have for example, a non-idempotent or non-reentrant API, and fail because it's pretty much impossible to deal with at the CSI plugin level, or your API is robust to it, and then everything just works. And then The last thing that we'd like to see from IPDK is, and I know I'm maybe going against the grain here, against sort of the stated goals of IPDK as I understand them. But we'd like to see do one thing initially and do it well. Meaning, I've worked on many projects that have tried to do everything for everyone, and it's rare when it succeeds. And even when it succeeds, there's a lot of pain along the way. It's usually much better to pick a limited subset of functionality, do one thing, but do it really well, and then expand it to other platforms, environments, and so on. Sorry about that. Forgot to put it on silent. So that's it. Thank you very much for listening to my wish list, and I'm really looking forward to where IPDK goes. And with that, I'm happy to take any questions.
Thanks, Muli. So first off, I'll let you know Dan Daly already stated that he's going to take your wish list and start a thread on Slack with these items. So he says thank you for that. Do have a couple questions. You listed a multi-step process in your slides, and in step 4, you use the term local block device. We have a question. Does that mean local SSD storage, or is that emulated?
Right. In step 4, there are no local block devices in the sense that there is actual, SSD flash. It means emulated local block device. So for the host operating system, it looks and feels like any NVMe device, but there are no, physical bits actually stored on that host. Everything is stored over the network.
Thank you. Okay, sure. Another question. For multiple Kubernetes clusters accessing the same shared pooled NVMe/TCP remote drives, would there be a benefit if the tenants of the Kubernetes system is included in the assignment of the target volumes or blocks? And also, is there an initiator IPU encryption to achieve both security in flight and reuse it as in security at rest?
Yeah, I do think that I didn't mention it, but LightBits is a multi-tenant system, and I absolutely think that not necessarily for multiple Kubernetes cluster, even for the same Kubernetes cluster that's shared across multiple tenants, multi-tenancy is definitely useful. And yes, encryption both on the network and on the data path, and also for data at rest, is definitely something that will be useful for many environments. Yeah.
Great. Question about keeping it simple. Question came in. Do you think having sub-projects with each specific focus that are part of a broader project that provides how to integrate the pieces will help with the scope issue?
That's a really good question. When I was preparing these slides, I've been thinking a little bit about OpenStack. I'll just come out and say it, both because we've just upstreamed the LightBits Cinder driver into OpenStack, but I've been working with OpenStack for over 10 years by this point in time. OpenStack has gone, I think, with this approach of sub-projects that do one thing well. It was good from the sub-project perspective, much clearer, goals for each sub-project. It made the user's life a lot more complicated in many cases. So obviously, just like there has to be some sort of division into different some things, but just taking 2 specific examples: OpenStack, where everything is done at an API level with different services that are developed pretty much independently. Or you could also think of the Linux kernel, where different subsystems work independently, but they're much more tightly together. So there has to be some sort of division, but the APIs and interfaces between these components, they need to be really well thought out, and it's ideal if you don't take it too far, because then the user has to mix and match lots and lots of different things just to get something to work. And that's what the user wants to do at the end of the day, get it to work. So yes, but, sorry, that was a bit long-winded. Yes, but.
Thank you.